Our topic is a group today. We'll define group and some problems we will be discussing today. Uh, Firstly, let's define group. Group. Let G be an G be a non-empty set and asterisk be a binary operation. Asterisk be a binary operation on set G. Then G comma asterisk under an operation asterisk is called the group if it satisfies the following axioms. Firstly, to be the group, let's define by G1 for this. This is closure axiom. If A comma B belongs to G, then A asterisk B belongs to G. This is closure axiom. And G2, that is associative. This is associative axiom. In this associative axiom, if A comma B comma C belongs to G, then A asterisk B asterisk C equal A asterisk B asterisk C. That also belongs to G. And G3, that is identity axiom. If A belongs to G, then there exists an element E belongs to G such that A asterisk E equal E asterisk A equal A, then E is an identity element. A is an identity element. And G4 inverse axiom, that if A belongs to Z, then there exists an element E belongs to Z, an element A dash belongs to Z such that A asterisk A dash equal A dash asterisk A equal to A, then A dash belongs to Z is the inverse of Z. So we have to verify the group. Suppose we will have given a set of the elements, some elements will be given in a set, then we have to verify whether that is group or not after fulfilling all these properties. If all these properties are satisfied, then that forms a group. So closure axiom, associative axiom, identity axiom, and inverse axiom. We have to check all. We have to check these all. Then if one is filled, then that is not a group. This is the format of group. And the second part, including, that is abelian group. Abelin, abelian group. That is also called commutative, commutative group. Yeah, that is also called commutative group. After verifying above four points or four axiom, we can check whether it is abelian or not. If it is given in only 2 marks, then directly you can write whether it is abelian or not using commutative properties. If you need to verify in 4 marks, all those condition you need to satisfy, and you need to take the last one. It depends on that. So or group Z comma asterisk under a binary operation asterisk is called commutative, commutative or abelian group if A asterisk B equal B asterisk A belongs to Z for all A comma B belongs to Z. This is called abelian group. Then let's move to the next part, that is about finite and infinite group. Finite and infinite group. A group that Z comma asterisk is said to be finite if G has finite number of distinct element. For example, G equal to 1 2 3. This is a finite group. And a group maybe the operation, we can write the operation as well. This is a finite state. Then asterisk, we can write that to be the group. Yes, only not that, we have to define okay, we can define this is a set, and the a dot, yeah, which one we try, let me check. If the elements are 1 2 3 and it is under the addition property. Now the second part, a group G asterisk is said to be, G has finite number of distinct elements. Yes, G asterisk is said to be infinite if G has infinite number of distinct elements. For example, is a set, yeah, or Z is a set of integer. These are the set of integers. Now moving to the next part, that is about trivial group. A group consisting consisting only one element is called a trivial group. The set Z equals 0 with usual addition operation. Trivial group and H equal only H equal to 1 with usual multiplication is a trivial group under multiplication. So above groups also you can define addition or multiplication, you can check that. I have given that. Now moving to the next part about the question, problem number 1, P1.
Sir, mathematically they have
It will be clear from some example as well. Question number 1 is, so that the set so that the set yes equal -1 0 1 does not form a group. Yes, but the what is the operation with respect to addition operation? Now operation is addition operation. So the solution, we have to verify does not form a group. We have to show solution. Here we have given set is -1 0 1. Yeah, firstly we have to check closure axiom. We have to check closure axiom. While checking closure axiom, here -1 0 and 1 belongs to yes, then -1 plus 1 equal to 0 belongs to yes, -1 plus 0 equal to uh, -1 belongs to x, and 1 plus 0 equal to 1 also belongs to yes, but 1 plus 1 equal to 2 does not belongs to yes. Hence yes is not closed under the operation plus. So one question that we have to does not form a group. If out of four axiom one is not satisfied, first is not satisfied, then others, if others are satisfied, that doesn't form a group. That's why we can conclude from this. If one two, so one is enough. Yeah, but we don't know first one will be satisfied or not, second or third or fourth, which will be failed, we don't know. But here fortunately first is failed, so we can start for the further process. You can check or you can practice for your understanding, but first is failed, then why need to check second? That will be the condition. That's why we can conclude from the uh, above condition, closure axiom does not satisfy fight, show that yes is not a group under plus operation. I have concluded here first question, and now move to the second question. Question number 2. Prove that the set of natural numbers does not form a group under loss operation. Interesting question. Now the solution for this question number 2 is, here we have given the the set of natural number, that is n equal 1 2 3 dot 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 dot. Yeah, and first we have to check first condition, closure axiom. For closure axiom, mm, for any a comma b belongs to n, a plus b also belongs to n. We can verify this uh, since 1 comma 2 belongs to n, 1 plus 2 equal 3 also belongs to n. Similarly, 1 plus 1, same element, suppose the lowest, equal to 2 also belongs to n. Hence, n is closed under the operation plus. I think in general, if we check, the sum of any two natural number is a natural number. That's why closure axiom is fulfilled or satisfied, or that under the operation plus. And now we have to move second properties or second condition, associative axiom. For associative axiom, uh, we have to check for any a comma b comma c belongs to n, a plus b plus c equal b plus, sorry, a plus b plus c belongs to n. Let's check from the real example also. It will be satisfied, we know that. Yeah, sum of any three natural number, the sum of first to the second any two numbers is the sum of first two and the second, that also belongs to n. That will be satisfied since 1 comma 2 comma 3 belongs to n. Then 1 plus 2 plus 3 equal 1 plus 2 plus 3 is what? 2 plus 3 is 5. 1 plus 5 is 6. And again, 1 plus 2 plus 3 equal, that also belongs to n. That 1 plus 2 plus 3 plus 3 equal to 6, that also belongs to n. Therefore 1 plus 2 plus 3 equal 1 plus 2 plus 3. Hence n is associative under the plus operation, or under the operation plus. That is also axiom, associative axiom also satisfied. And now third condition about identity axiom. For identity axiom, we have to suppose an identity element first. let E be an identity element. E be an identity element, then 1 plus E equal to 1. Just simply the number and identity elements is the number itself. So 1 plus equal to E, that implies E equal to 0. Oh, 0 does not belongs to N. Hence, identity axiom does not satisfy under the operation plus. Therefore, third axiom is not satisfied. Therefore, what we can conclude is N is not a group under the operation plus. So in this way we can verify the second, or we can prove the second question. Third number question is, yeah, show that the set t equal minus 1 comma 1, t equal minus 1 comma 1 forms a group under multiplication operation. So the solution for this question is, firstly here we have given say t equal minus 1 comma 1, and firstly move to the first properties, closure property or axiom, closure axiom. Since minus 1 comma 1 belongs to t, then minus 1 dot 1 equal to minus 1 belongs to t. Hence t is closed under the multiplication of operation. We have only two elements, then their product is also belongs to the same set, multiplication operation. So closure property is satisfied. Now move to the second part, associative axiom. Associative axiom. For this axiom, we have only two elements. Anyway, we can take, since minus 1, 1 and 1 belongs to t, then let's operate 1 minus 1 dot 1 dot 1 equal minus 1 dot 1 equal to minus 1, and minus 1 dot 1 dot 1 equal minus 1 dot 1 equal to minus 1. Therefore minus 1 dot 1 dot 1 equal minus 1 dot 1 dot 1. So this condition is the same result we obtain. Both belongs to t. Yeah, both belongs to the same set. Hence t is associative. T is associative under the multiplication operation. Under the multiplication axiom. This part second also we have checked. Now we have to move to the third property, that is third condition. What is that? That is identity axiom. identity axiom. For identity axiom, we have to suppose an element. Let E be the identity element. Then -1 dot E equal -1. This implies E equal to 1, which is also belongs to T. Similarly, 1 dot E equal to 1. This implies, because the product of the two identity element, the same element, result is the same element. That's we have many times repeated that. The duita ko product त्यही हुन्छ. Then what is E? E equal to 1. That is also belongs to T. So from this checking, or from this condition, what you have to, the value of E is 1. Hence, E equal to 1, identity will be the same element. E is equal to 1 is an identity element. Therefore, existence of identity element is satisfied. Now the fourth and the last property is inverse axiom. Inverse axiom we need to check. For that, we have to suppose the inverse element. Let A be the inverse element. Then what the condition is? 1 minus 1 dot A equal to E. The product is that should be the identity element. One element and the identity inverse element, their product is E. So this implies minus 1 dot A equal to, what is the value of E? That is 1. That implies A equal to -1. That belongs to T. Similarly, by taking another element, 1 dot A equal to E, this implies 1 dot A equal to 1, also implies A equal to 1, that also belongs to T. So both belongs to T. So both have inverse element. -1 and 1 have both have inverse elements. Hence existence of inverse elements is satisfied. Element is satisfied. Therefore all the four conditions, all the four conditions are satisfied. All the axioms of group are satisfied therefore the set T equal -1, 1 is a group under multiplication operation. Under multiplication operation.